Hello guys, welcome to another video. This video is actually me going over USACO silver contest. Let me try to get that in. Wait, where was the contest? Wait, where did they move it? They had a contest. It would be nice if I can access the problem text. Um, I guess they just hide it when they're marking it. Anyway, I'll go over the problem. So what I solved is P2 and P3, so I have those two files open. So I'll explain problem for problem 2. So basically, this assumes that you know what the problem is, because otherwise, why would you be watching this video? But anyways, so I'll just go over, so these are the criterias. So the way you do it is you literally just simulate the process. So at the beginning, you put everyone who's qualified in, and they set up some additional information so that when you remove someone from the contest, you can efficiently move them in. So let me just zoom out. So I guess what I would do is let's say this has capacity of 4, and then let's get a few more people in here. So this also has capacity of 4. Yeah, so let's say we have this participant. So he's rank 9. He wants to be in both of these criteria. So what happens when you remove this guy? Well, basically you put him here. Now the way you can do it is you can use a queue for each criteria. So these are the people who qualified, and then you have some queue. You have some queue that's the people waiting to be qualified for each rank. So um let's do this. So when we remove a guy in a criteria, we look at its queue, we pop out the first element, and then we put that in. Okay, so now let's assume that this guy is in, right? We still have 4 people. So this guy, he wants to be here, but he also wants to be here. So what happens when you remove this 4? Well, we have to move this guy here, and maybe then number 10 will come here. So basically what happens is we put this number 9 guy on the queue for both of these. So when we put him in, we remove it. Remove him from this queue. Wait, so the queue looks like this. So 9's in here, so we remove it. So now when someone leaves, because we go through these criteria in order, we see that this 9 is qualified to be moved in. So we then basically have to move this guy. So then this is out of the queue, and number 10 can replace him. So it's this process of queuing. So basically what I did was I sorted out each criteria, and then basically this is me. This is before someone leaves, so I set up the necessary information. Now when someone leaves, I basically, so this qual C, it keeps track of the criteria they qualify for, and then So if they're qualifying something, I remove it, and I remove it from the global answer. And then I have to check that queue because I left a spot there. So if someone's in there, then I'm gonna move it. But this process happens repeatedly because you can keep shuffling people down to higher criterias. So we have to keep checking those criterias. And this actually runs in linear time because when you see someone gets queued for certain criteria, you're basically going through their list of things to qualify for. And you do that for every person. So even if you shuffle one person down to each criteria, it's still only going through the things they qualify for. So yeah, that's problem two. It's pretty tedious implementation. But let's move on to problem three. So problem three is well, I guess I'll not erase it yet. The idea is let's say I have the numbers. So let's say S is equal to 1, 2, 3, 4. So if I have like I don't know, I guess. So the idea is let's just fix our index I for now. So there is four ways you can do this, which basically boils down to two, but I expanded four for simplicity. You can either go just right, or you could go just left, or you can go to left and go to right, or you can go to right and then you go to left. Because you basically never switch the direction twice, otherwise you're going in the same direction. But like, yeah. So I will not be going through a case where you go left or go right because they're are trivially handled by the other more complex cases. If you just go right, then it's basically same as going left 0 steps and then go right. Okay, so now let's say this guy he goes to two, right? So he goes to two, and he has to go all the way here. So this is 2 plus 4 steps. So this is 6 operations. And then if he goes down to one, well, he has to go even further. So that's that's 8 operations for this. But if he goes here, well, it's impossible. So what the point here is that let's say if he goes here, well, you don't want to go. You only want to go right as far as necessary. Then you stop, right? Because you don't need to include this extra four. Like this is just a one operation extra. The same story applies with the one. You only need to go so far. And we can actually compute how far to go right for every index in linear time. So let's say this is -1. -1 means that you can't include every single occurrence of you can't include every number once. So this is -1, -1, -1. So how far does this go? Or you can just keep track of index you go to, which I do. So like this is just two passes. I do this for every direction. I'm not going through the solution as if we're gonna go to right because you can mirror the logic for left. Like the logic is pretty much the same. One, two, three, four. So this goes to index 6, and then this goes to index 6 as well. So this is to the right. So that means you have right of 1 is equal to 6. So what happens if we go to index 2? Well, So this is I equals 4. So what's the number of operations? If we write it out as a formula, then we have and let's just call this next j. So I minus j plus, so then we have r of j minus j plus 1. So that's the formula if you were to fix some index. Now, of course, we can't literally go through all the options and calculate it this way. We somehow have to decide where to go for a linear time solution. So then we look at the formula again and see what variables change. Well, these all stay the same. So this is this is constant. So only our index changes. So what we can use, we can say we store this as another value. Let's call this x. So all we have to do is, oh, I should expand this to include this negative sign. So all we have to do is when we add index I and we have this variable x, then we just do I plus x. Right. And then of course we can iterate through the index in linear time, so we just have to keep track of this x. And since we want the smallest possible amount of operations, we want to minimize this x. So we basically compute this x for all of these indices, given that they're not -1. So this one, so this x is equal to, so this is 6 minus 1. 6 minus 1 is equal to 5. And then this x is equal to, um, oh, this is actually 5 minus 1. Oops. Let me just correct it. Well, I'll just write 7 here. So this is x equals 7 at this index, and then you have x is equal to 4, 2. So then when you go along this path and go in this direction, you can actually, given that you computed this R array that tells you how far to go for every index, then you can update this x in linear time. So then like I'll say x of 2 plus I is equal to, well, this is just 2 plus 4 is 6, which does mirror our answer, and then you have x of 1 plus I is equal to 7 plus, wait, I think that's wrong. Oh, this is supposed to be 4. So 4 8. So which does match if you were to brute force these manually. So you just have to keep track of minimum x once you go through this way. Now you also have to go the other way as a separate pass because you can't just say like if you look at the left array, right? You can't just say this is 2 just because this guy here's just because this guy here reached it. It's not necessary. Well, it's like there's some case where like this duplicated for like it will mess with you if you just base it off of a R array. So that's pretty much the solution though, is you just calculate this x for all the indices and you minimize it. It'll work out because yeah, it will just work out. Yeah, that's the solution how to do it in linear time. Now as for the code, Now, given that the array is cyclic, I just appended the array to itself. So I get 2 times n for the length. And then otherwise, this is the path to the computer left array and then the right array. And then I go through both directions again, and you can see I just set minimum min. And that's pretty much it.